Resting membrane potential is the electrical charge difference that exists across the plasma membrane, both inside and outside the cell. You can kind of think of it as a salty banana where there's going to be more potassium on the inside and more sodium on the outside. The value inside is going to be negative 70 millivolts because it is not receiving any communication or an electrical signal. It's just ready to receive that stimulus. So during resting membrane potential, to maintain the value inside the cell at negative 70 millivolts, the neuron uses a sodium-potassium pump to make sure that there is a higher concentration of sodium outside the cell and a higher concentration of potassium inside the cell. So typically there will be 3 sodium ions that will go back outside, and there will be 2 potassium ions that will go inside the cell. And this happens continuously to maintain that negative 70 millivolts. Even though both ions are positively charged, the inside of the cell tends to be more negative because potassium will kind of contend with the more negatively charged proteins inside the cell. Potassium ions tend to diffuse out because they are more permeable, and the sodium ions kind of are a little bit slower to diffuse back in because it's less permeable. Local potentials are small changes in the electrical charge of the plasma membrane. The purpose is for the resting potential to get closer to threshold and eventually trigger the action potential. So when the dendrites get stimulated, these sodium gates will open, and it will allow sodium ions to diffuse from outside the cell into the cell, and this will cause the shift in the membrane potential to be more positive, and that's called depolarization. Sometimes if the stimulus is strong enough, it can go from negative 70 millivolts and reach the threshold potential of negative 55 millivolts. So local potentials will have 3 characteristics, one of them being that they are graded, which means that it will vary in magnitude depending on the strength of the stimulus. So the more stimulation that occurs, the more the sodium channels will open, and then there's going to be more sodium ions that will go into the ICF. If this happens, then it can reach the threshold of negative 55 millivolts, and then that can trigger action potential. They're reversible. If the stimulation stops, then the membrane will return to its resting membrane potential. And this usually happens because the sodium gates will close without the stimulation. And then the sodium-potassium pumps will return the sodium ions back out into the cell. Local potential is also decremental, meaning that the current gets weaker the farther away from the site of the stimulation it gets. So during local potential, the stimulus will try and go from negative 70 millivolts and try to reach negative 55 millivolts to reach that threshold potential. If the signal is strong enough, then it will trigger action potential, and then that will get it to the positive 35 millivolts. Sometimes if the signal isn't strong enough or the signal stops, it will kind of go back down to that resting membrane potential. So once this negative 55 millivolts is reached in the axon hillock, it will trigger action potential. Once that action potential starts, it's going to keep going in the axon body until it reaches the axon terminal. So when this threshold is met, the voltage-gated sodium channels will open and sodium ions will rush into the axon, causing a depolarization, meaning it will make the inside more positive, and this will keep going until it reaches a potential of positive 35 millivolts inside. When it reaches positive 35 millivolts inside the cell, the sodium channels will close and potassium channels will open, allowing potassium to leave the cell, meaning that it will repolarize, causing the inside of the cell to become more negative. Sometimes it can go down even further than negative 70 and go to negative 90 millivolts, and that's called a hyperpolarization. So once that action potential finishes in one area, it will continue moving forward down the axon until it reaches that axon terminal. So during resting membrane potential, when there is no communication and it's just waiting for a stimulus, it's going to be at negative 70 millivolts. And then during local potential in the axon hillock, if there is a strong enough stimulus, then it can reach that threshold of negative 55 millivolts and trigger the action potential. Once that starts, it's going to depolarize and allow the sodium to go in through the sodium channels until it reaches that positive 35 millivolts. When it reaches that positive 35 millivolts value, the sodium channels will close and the potassium channels will open, allowing the potassium to go out of the cell, meaning that it will start to repolarize. Sometimes it will even go further than that negative 70 down to negative 90 millivolts, and this is called hyperpolarization. This is when the sodium potassium pumps will help it get back to that resting membrane potential of the negative 70 millivolts.